Okay, so last week I owe you both the explanation on how we can choose the sorting algorithm that is um, actually related to this factor. Okay, so there are one, stability, and then complexity of coding and other programming language use, and the nature of the dataset. There are three explanation that I owe you both. Okay, so first, when we are choosing the sorting algorithm that we have learned previously, we have said that in our notes previously, the best, the traditional one, which is the example insertion, selection, bubble, we said that it is slower than quick sort, merge sort. Okay, but actually it is not all of the time the merge sort or the quick sort is better than the slower algorithm. For example, the bubble or insertion or selection. Okay, so we cannot say that all of the time quick sort is better, the best. It is suitable for all of the condition. So no. Okay, so we have I have explained about speed, consistency of performance, memory requirement, and versatility of handling various data types. But I didn't explain about the stability and the complexity of coding and the nature of data set. Okay, so when we are choosing the sorting algorithm, it is actually depending on the stability. So what does it mean by the stability? So stability meaning, let's say you have already a list of data that is actually already sorted based on their name. Okay, so imagine you have already a set of data that actually already sorted based on their name. For example, student name, student list. So it is already sorted based on the name of the student. But besides, we want to sort them by using the name of the student. We want to also sort that list first. For the first sort, it is by using the student name as it is the original list. And then the second sort, we want to sort beside it is sorted based on the student name. We want also it is sorted based on the grade. Okay, so when we have this type of condition, so we should not use, for example, the quick sort, because quick sort it can sort the list not based on their natural way. Okay, so if we found this type of condition, we want to sort, meaning the condition where we want to sort the list still based on the student name, but the second sort we want to sort it based on the student grades. So if we found this type of condition, it is better if we didn't use the quick sort for the second sort. So it is better if we are using the most stable sorting algorithm, for example, insertion sort. Okay, so it is called as a most stable uh, most stable sorting algorithm. For example, of the most stable sorting algorithm is the insertion sort, okay, and merge sort. The one that is not really stable is actually the quick sort, because quick sort can sort the data based regardless of their natural way of natural sorting of that data. So we afraid that the second sort will make the first sort, which is by the student name, will be kena kacau, meaning it won't be sorted based on the student name anymore if you are using the second, if you're using the quick sort for the second sort. Okay, so that is the stability. So the one or sorting algorithm that is known as a stable is, for example, the insertion sort and merge sort. The quick sort is considered as unstable, and then it is not suitable with the condition like what I tell just now when we meet this type of condition where we already have the list sorted based on the name, but the second sort we want it is based on the grade. First sorted based on the name, and then second sort we want to set it based on the grade. So because we don't want to change, we don't want to disturb the first sort, so it is better if we didn't use the unstable sorting algorithm, for example, quick sort and heap sort. But heap sort actually we didn't cover in this chapter. Okay, so clear about the stability, how we choose our sorting algorithm based on the stability.
Yeah.
Okay, so for the complexity of coding and other programming language, so there are some programming language that actually having their own library of sorting. For example, PHP, almost all of the programming language has its own library. So Java, we know that it has a lot of sorting library as what we have learned now. Okay, it has iterator, it has collection, but that type of library is not necessarily to be available in another type of programming language. So we cannot use all of this sorting, all of the sorting that we have learned in this data structure course in another language. For example, in PHP, maybe in Python, because that type of library, doesn't created. It is not available in that language. So it is better if we are using the sorting that is available in that programming language library. So we use their existing sort library. So because if we want to implement like all of the algorithm of sorting that we have learned previously, it might need you to create your own library, or you will create your own library or your own class program just to do the sorting that we want. For example, if you want to implement quick sort or heap sort using PHP language, but that type of library is not available in PHP, then what you can do, if you still want to use the quick sort in PHP, then you need to create your own library. You need to create the classes, the object, and then the library like what we using in our Java, but it is written in PHP language. Okay, so that's why if you want to use sorting algorithm that is actually a little bit different from the traditional sorting, like the insertion, selections, for example, this quick sort and heap sort So usually you cannot use that algorithm in another language because doesn't exist. There are no people or programmer that develop that library yet. Okay, so the best way is you use the sorting method that is already available in that programming language that you want to use. Okay, so clear about the complexity of coding, how we choose our sorting algorithm based on the programming language.
Oh yeah.
Okay. So for example, if quicksort is not available in PHP, then you need to use more traditional sorting lah. So usually the sorting that is available in all of the language is the one that is traditionally used. For example, the bubble, the selection, the insertion. Okay. So and then the nature of data set. They are actually when we are not all of the sorting algorithm is available for all of type of the data. Okay, so for example, this the data is different in the structure of the data. For example, the data that is used to to do the topological. Topological is the data that is used to do a graph node. So this type of data, it is not suitable if you are using the traditional sorting algorithm. For example, the bubble, insertion, selection. So we cannot use this type of algorithm to sort the topological data. Okay, so instead we can use some sorting algorithm that is not based on comparison, because all of the algorithm that we have learned previously, it is comparing object one, object two, and then comparing first element to the second element. So there are also an algorithm in sorting, but it is didn't implement any comparison. So the example of sorting algorithm under this category is radix and counting sort, but we didn't cover it in this chapter because um, it is more complicated lah. So for now, we know it is enough for you to know that there are a data type of data that cannot be sorted based on the comparison based algorithm. So the comparison based algorithm is all of the algorithm that we have learned previously. So the example of non-comparison based algorithm is radix and counting sort, but we didn't cover that two algorithm in this chapter lah. Okay. So clear about the nature of the data set?
Oh yeah.
So Kelvin? Okay, thank you. So we proceed to our chapter 9, the binary tree. Okay, wait, I drink first. So this chapter, we will cover it in 2 weeks. So this week 10, and week 11 next week. Okay, so for this week, we will study about the binary tree. Binary tree. So we will learn about what is binary tree in our next slide. So this is the topic that we will cover. First, the application of the binary tree, such as expression tree and decision tree. Yeah, so there are two examples of binary tree applications that we will cover. And then how to implement the binary tree and binary search tree. And then also to discuss the factor that affect the efficiency of binary search tree operations. Okay, so I think this one we will cover next week lah. And then maybe some of the topic in this topic too. So maybe we will only cover up until implementing the binary tree lah. Okay, so how to implement the binary search tree, maybe we will cover on next week. So depending on our time today lah. Okay, so what is actually the binary tree? Okay, so because we will learn about expression tree and decision tree later, but before that, what is actually the tree concept? So what is binary tree? So all of the data that you have learned previously, okay, so it is in linear order. Okay, so all of array list, it is all in linear order. Okay, so what if we have a data that is actually in hierarchy? There are some organization, there are subgroup and grouping. Well, so what if we have that kind of data? Okay, so that's why we are using three concepts in doing that's why we have a three concept in our Java programming, because it is to supply, or it is to to supply this type of data. Okay, how we can code it faster lah. Okay, so some data organizations require categorizing data into group and subgroup. So this is what we called as hierarchical classification. Okay, so data item appear at various levels within the organization. So just imagine lah the hierarchy. For example, organization chart, or parents child chart. Okay, so that is the hierarchical chart lah. Okay, so these three concepts provide hierarchical organizations in which data items have ancestor and descendant. So they are ancestor, they are descendants, they are parents, they are child. Okay, so this type of organization, this type of data is richer and more varied than any other additive. Okay, so if you remember, all of the data that you have learned previously is in the linear data. It doesn't have any parents, it doesn't have any child. Okay, so by using these three concepts, we can operate that hierarchical classifications data in more better way. Okay, so these are the example of data that can be implemented in code using the tree or the binary tree letter. Okay, so for example, the family trees lah. For example, Carol has three child, Brett, Jennifer, and Brian. Brett only have one child, Susan. Jennifer have two child, Jared and Jamie. Brian doesn't have any child. Okay, so this type of information can be used, or can be implemented, can be coded using binary tree. So we'll learn about that later. Okay, so another example of data is the organization chart. For example, for a company, there must be a president. Under president, there will be three vice presidents that help the presidents. And then under each of the vice presidents, there will be another department. For example, here lah, Dean of Art and Sciences. The child is the computer science, and then there are Dean of Business, Dean of Engineering. Okay, so this is the example of organizations in university and administrative structure. Okay, so another example is file directory. So for example, in your file, in your D, for example, you have one folder, which is my stuff. And then under that in that folder you have another folder, the folder that for home, for work, for play, your game, okay, for school. Okay, so this also can be, this type of information also can be coded using the binary tree. Okay, so this is the example of computer files organized into folder. Okay, so the three terminology. So here are the three, the terminology that we need to learn, the term that we need to understand before we learn further about this binary tree. Okay, so a tree. Tree is a collection of nodes. It is connected by edge. So that edge is the links, the line that connected one node to another node, and then the nodes are arranged in level in a hierarchical manner. So we will see later lah the graphical representation of a tree. So the edge indicates the relationship among the nodes. The edge is the links to the line that connected the nodes, that connecting the nodes. Okay, so the top level is a single node called the root. So the first node at the top called as a root. Okay, so if we see this, at the top is what we call as the root, the parent, the ancestor. Okay, the moyang. Okay, so the ancestor or this root will be in level 1. So all of the line that connected the ancestor to its child, the child to the grandchildren, to its child, all of this link lah, all of this line is called as edge. Okay, so a tree is the collection of a parent and its child. Okay, so this is what we called as, all of this actually a tree. All of this is a tree. All of this. But when we have another tree like this, we call it as a subtree. Okay, so far so good.
Okay.
So the node that doesn't have any child, for example, N or P, G, H, Q, R, S, T, L, and M. It doesn't have any child, so we call it as leaves. Okay, so this tree is divided by level. First level is the root. The child of the root is level 1. The child of the grandchildren of the root is called as a level 3, and then the grandchildren of the root is called as a level 4. Okay, so this is still the term that we need to learn and understand about the binary tree. Okay, so the nodes at a given level are children of nodes of the previous level. Okay, so yeah. The nodes at given level are children of nodes of the previous level. This is the children of air. This is the children of level 2. Okay, so this level is the children of level, this one. So each of the level is actually the children of the previous level. All of the nodes in level 4 is actually children of the nodes in the level 3. Okay, so a node with children is is the parent node of those children. Okay, so we know that here A is the parent of B, C, D, and E. Okay, so node with the same parent are sibling. All of the nodes here is, if it is have the same parent and it is in the same level, it is called as a sibling. But here the siblings here is F and G lah, because it has the same parent. It is not the siblings from all of the child and from this level lah. Okay, so this is easy lah, because we know it is similar with our what, our hierarchy, the family hierarchy. This is the cousin lah, cousin for F and G. H is cousin for F and G. Okay, so a node with no children is a leaf node. Okay, like I said just now. Okay, so the only node with no parent is the root node. Okay, so the only node that with no parent is the root node. Okay, so a node is reached from the root by a path. Okay, so what is path? The path is the length of the path. The path is actually the number of edge that compose it. Okay, so this is the path, meaning the length. So from A to F, the length is 2, 1, 2. There are 2 edge. The height of a tree is the number of level in the tree. So in this example, there are 4 levels. So the height for this tree is 4. Okay, so after that, the subtree of a node is a tree rooted at the child of that node. Okay, so this is the subtree. Okay, so what is the binary tree? Okay, so a binary tree is a tree in which each of its node has at most only 2 children. Okay, so each of the nodes here, from here until here, all of the nodes here at most only have 2 children. So for this type of tree, this is not binary tree, because there are some nodes here that has 3 children. For example, F 1, 2, 3. It have 3 children. D also have 3 children. I also have I is only have 2 children lah. But this tree is not considered as a binary tree because it has more than 2 children. So we call this is a general tree. It is not binary tree because it has nodes that has more than 2 nodes. Okay, so we only categorize the tree as a binary tree if each of the nodes in that tree only has at most 2 children. For example, this. Okay, so binary tree is either empty or has the following form. Okay, so this is the form. It has root, it has left, 3 left, or 3 right, where T left and T right are binary tree also. It must has at most 2 children. Okay, so the height of the binary is 1, 2, 3 because there are 3 levels here. Okay, so 1, 2, 3. 3 levels. So 3 traversals. So now we are proceeding to these 3 traversals. These 3 traversals is actually the process of the code, the process of code that is actually how it will visiting or stepping through the nodes in the tree. Okay, so either it is from the left to the right, either it is top to down. Okay, so how the process is visiting how the process or algorithm in our code is visiting each of the nodes is what we called as a traversal. Okay, so each node in the binary tree is visited or processed exactly once during the traversals. Okay, so in one round of traversals, each node will need visited once. Okay, so what does it mean by the visiting a node? It is to process the data within the node. Okay, so each of that node is actually it containing some process, some code. So when we are going to that node and then we go run through all of the code inside that node, it is called as visiting that node. So in the traversals, each of the node that is um, declared in the code must be visited exactly once. Okay, so a traversals can pass through a node without visiting it at the moment. Okay, so it must be visited later, but sometimes it can only pass through that node without visiting, meaning without processing the process inside it. It only see a little bit, sekejap, sekejap, and then it didn't go into that code, but it passed to the another node. Okay, so the traversal is the process of visiting each of these nodes. Some of the traversals we will learn later. Okay, there are three. There are three type of traversals that we will learn after this. Okay, so the first type of traversals is pre-order. Okay, so how does this pre-order traversal? Okay, so the rule for this pre-order traversals is the root must be visited first. Okay, first must be the root. Second is the nodes from the left. Okay, so the third is the nodes from the right. Okay, so that is pre-order. Okay, for example here, number 1 is the root, and then second that will be visited is number 2. And then after that, remember, it will need to visit all of the nodes that is from the left after the root. So here after 2, it going to the 3 because it is from the left. And then after that, it didn't go to the right, but it directly go to the left. Okay, so 1, 2, 3, 4. And then after that, baru it go to the right. Okay, this is the 5th node. It will visit. This is also the 6th nodes. It will visit. And then after that, then it visit the nodes at the right. Okay, so remember the rule is left first, baru the right. So here 7, there are 2 nodes. It go to the left first and then to the right. From here it has 2 nodes, then it go to 10 first, then baru pergi 11. Okay? So understand this pre-order traversals, root first, left, baru right.
Okay.
So the second type of traversal is in order. We call it as in order. So the difference between this type with the previous type is the root will be visited after it visits the left subtree. Okay, so here the first will be visited is the left first. And then after that, then go to the root. After the root, then go to the right. Okay, so here see this the not structure lah the sequence of visit. Okay, so first must be one, and then remember when you find the left, you need to go to the root. Okay, so that's why its root is 2, and then go to the right. Okay, so after that, we go to the root again because here is left. So we go to the left, to the root, and then go to the right. Okay, here, and then here is already cover the subtree, another subtree. Okay, so after that, it go to the root, and then baru pergi to the right. But here, there are subtree, so you didn't go from here to here, but instead you go to here because the rule is root from the left. So that's why after 6 here, it go to here. Okay, after that, it start, it go to this 7, then it go to the root of this node, and then after that, it go to the right. But it will not go to here. It will go here. Because remember, the first rule is it need to visit left. Left, root, right. If the previous, it is root, left, right. This one, left, root, right. Okay, so the third type of traversals is post order. So here, as the name of it, you know, pre is before, in is meaning in the middle, and then post is after. So, this post order traversal visiting the root after visiting the subtree, meaning it is the last node that will be visited. So, pre, in, and post is actually referring to the sequence of when we will visit the root node. Okay, so pre is we visit node root first. That is which is meaning the first is the root. In meaning we visit the root after in the middle lah, inside in the middle of the tree. And then after that, post, we visit the root as the last node, as the last destination. Okay, so visit all the nodes in the root left subtree first. And then after that, go to the right. And then after that, baru visit the node, the root. Okay, so all of this rule not only it is actually applicable in each of the subtree, not only to the last root here. So, for example, what I meant was here, 1, left, right, root, left, right, root. And then after that, from here, left, right, root. Okay, so after that, because here it has another child, weird. Yeah, but that is um, another type lah. It is actually alternative on how to choose how to choose or access the nodes that you want to access. So actually, um, um, it is actually not all of these traversals type, right? It is it will be suitable with some scenario. So it is not that only pre-order is better, only in order is better, only post order is better. So all of these types suitable to some type of scenario. So we will see later how we can um, apply this type of traversal later. So that's why we will learn later about the application of the binary tree, which is the expressions tree. Okay, so we will learn that later. Okay, so remember for this, left, right, root, left, right, root. So because here there is still nodes from its right, so that's why it didn't go directly to here because there is still here that still need to be visited. So after that, here 5, after 5 it will go to 6 because left. Okay, so after that it will go here. It is not going here because left is still not finished. There is still nodes from the left. So 6, 7, 8, baru 9, baru 10, baru pergi 11. Okay, so this is the summary lah of I already shared it with you guys, but this is the link lah. So this is the Jamboard, the summary of the 3 types of traversals. Okay, so yeah, so this is the pre-order, this is the in order, this is the post order. Okay, so remember pre-order, it must visit the root first, and then left, and then right. For the in order, it must start from the left, root, right. For the post order, it must finish all of the child first, left and right, and then baru it go to the parent. Okay, so this is the summary lah. We can refer to this letter. Okay. Okay, so level order traversal. Another type of traversals is level order, meaning it is visiting each of the node based on the level. Okay, so this type of traversal, it will begin at the root level and then it will proceed to the next level. It will visit nodes one level at one time. Okay, so for example, it will start at the root, and then after that, it will go to the next level, but left first lah. 2, and then baru go to the right, and then after that, 4, 5, 6, 7. So it is based on the level, but left first. Okay, so at 9, 10, 11. So this one is easy to understand. Kan? So understand this level order, post order.
Oh yeah.
So yeah, in my Jamboard, I didn't include the level order. So actually there are another level order. It is not only three. There are another which is level order. But later lah I update this. Okay, so for this one. So looking at this number, I will give about I give 15 minutes for you to finish this. Just write the number which it will visit first by using pre-order, in-order, and post-order. Okay,
Okay.
so try first. I give 15 minutes. So remember this. Yeah, you cannot see. Dekat ni. Your Jamboard. You already can access that Jamboard, kan? So you use that Jamboard. Use this Jamboard.
We view only, we cannot edit, I think.
Oh, you can, but you can view, right?
Yeah.
Okay, so view first lah. View first, and then based on this order, you write the structure first. I mean, write which number will be visited first.
Oh, we just write a number in order.
Yeah,
Okay.
yeah. Following these three orders. Okay, so I will give time until 3 minutes. Refer to the Jamboard. Just write it. For example, if 2 is visited first, then 2, 1, 3, 8, something like that lah. I saw Noel already, but we check later. We wait for Kelvin first.
Done, Miss.
Okay, done. Okay, we check okay, so pre-order 11 at 3, 2, 1, 5, 4, 6, 10. Okay, correct. Both Noel and Kelvin. In order 2, 3, 1 at 4, 5 at 4, 5. No, Kelvin wrong already there. So at 4, 5, 6, 11, 9, 6, 11, 9, 6, 11, 9. So yeah, so Kelvin also wrong at that. 11, after 11, we should be 9. Baru 10, baru 7. Okay, so honestly, when I tried this previously, I also same with Kelvin lah for the in order. Okay, so for the post order, it is 2, 1, 3, 2, 1, 3, because it is 2, 1, 3. And then 4, 6, 5, 4, 6, 5 at 9, 7, at 9, 7, at 9, 7, 10, 11. Okay, so only yang in order lah got a little bit wrong. Okay, so Kelvin, don't worry, I am also the same. I made the same mistake with same as you lah previously when I tried. So in order, it must be left, right, then baru the node. So that's why 2, 1, 3. Sorry. In order, the root is in the middle. Okay, so left, root, right. Okay, so that's why 2, 3, 1, 2, 3, 1. And then after that, it will go 2, 3, 1, and then it go to the root because there are no more left or right after that. So that's why it go to the root. So after that, start with the left root, right. Okay, so that's why 4, 5, 4, 5, 6. Okay, so after that, proceed with the top because there are no more at the right. Okay, so that's why we go to the 11. After that, remember, Kelvin, it is not going to the link that is, it doesn't, when you do this it doesn't need the node is linked. Okay, so no need to be linked. For example, here for the in order, it will go to, from 11, go to 9. Even though 11 and 9 is not directly linked. Okay, so that's why it go to after 11 and then it start again left root right. So that's why 9, 10, 7. Okay, Kelvin?
Okay, Miss.
Okay. So reconstruct a unique binary tree for the following traversal output. Okay, so here you reconstruct. Meaning here, given the number, you draw the tree. So you can use the Jamboard. Please use the Jamboard to draw. Wait, I give the access first. Okay. Okay, so create another page. Wait, I forgot already how to create another page here. Okay. Oh, here. I just go move to the first page is Noel. Sorry, the second page is Noel. Third page is Kelvin. Okay, so you can access that. I will share this. Okay, so pre-order and in order. Sorry. I think pre-order Noel, in order Kelvin. Sorry ya.
Okay.
Uh, So done.
Yeah.
Noel?
Done lah. Yeah.
Why? You sounds like not confident.
Yes, I forgot to put number 5. Yeah.
Yeah, I noticed. Yes, I noticed you forgot to include the number 5 lah. So it should be where? The number 5.
Actually, I'm not sure.
So it should be under this. Under 4.
Oh,
Because this is pre-order, right? Pre-order, remember? It is root, left, right. So here, start from the root. Where's the number? It says 6, 4. Yeah. Better like this. Okay, so 6, 4, and then it must be go to the left. 6, 4, 2, 1. Okay, so after that, baru it go to the right. 3. And then after that, go to the here, 5. Here, it is under 4.
oh.
All are correct, but only you left 1. Here, 5.
So I put now?
Yeah. No.
Oh.
Okay, so for Kelvin, in order. Wait, so in order, left, root, right. So that's why left, root, right. And then go to the root because there are no more left. So that's why 4, 5. And then after that, go to 6 because there are no more left. And then go to the most left, 7, 8, 9, 10, 11. Yes, correct. Okay, so in order is correct. So let's see in our, because here only one answer. So we check either it is for pre-order or in order. One, 2, 3, then 6, and then 8, 7, I think this is in order, answer for in order, but it is like this. Wait, 8, 7. So we are correct up until 8, 7.
This is pre-order, I think.
Pre-order kan ni? No, pre-order it should be yeah. Wait, yeah. Correct. This is pre-order. Yeah. So this is pre-order, but we are correct up until 8 and 7. Here it connect. Wait, why is it after 7? 8, 7. Pre-order. First. Then here. And then
Could there be multiple answers for this?
yeah, I think for this, I think it can be another
Could it be the 3 must support both? pre-order and in order.
Oh, that one I'm not sure. Either I think no lah, because usually because pre-order and in order it is visited in different way, in different order, not different way, in different order. So I think this is not answer for both lah. But this is either, but I think it is more to pre-order. But I think um Noel pre-order and this pre-order are both correct because as long as
But
we
if this is in order, also correct, isn't it?
in order I think it is a little bit different lah because in order it is like yours. I mean, yeah, it is
Well,
like
if you
your,
if you check the in order following this answer, I think is one also correct.
yeah, beta. Your double, your Gembot. Where is Gembot? This one. My in order same with Kelvin lah.
Yeah, but I think this table also can satisfy the
This diagram also can satisfy the in order, you mean?
this tree also can satisfy the in order, I think. If you check.
For example, after 6 lah, after this 6. Okay, so after this 6, after this 6 for in order, after 6 lah, but because all of the left is correct for pre-order and in order, right? It is the same structure for pre-order and in order. The only difference is the right nodes, the right subtree. Okay, so after 6, for in order it must be left, root, right. And then now we go to the right. Okay, so in order it is here and here. And then 7. 7, it must go to here also, yes. 7, after that 9. 7. So it must be left, root, right. But here, if you go from 6 to 7, yes, it is correct. From the root, meaning pergi here. And then
Isn't
after here, it should be, beta, from here, it should be to the root. Because here, we start at the left again, then left, root, right.
Should it be start at 9 and then 7? If it's like
Yeah, yeah.
Okay,
So
okay.
here should be 9. That's why my answer also here, kan? I don't know if you all can see, if you can see lah.
Cannot.
Beta.
It's fine.
Yeah, yeah. But you understand lah, kan? Because 9 it should be here. 9 should be here because we start at left again. So left, root, right. Then that's why after 6 here, we are now in 7 here, which is left. So left, root, right. So 9, left, root, right. So that's why left here should be 9. Here should be right. And then after that, go to the left again. So left should be, I will put in the Gembot lah, easier. That is the Gembot. How many windows I open? Okay, that is the Gembot. I cannot find my Gembot already. Oh, here. Right? But I close first. I open again lah Gembot here. Can copy paste kan?
Cannot.
Can 7, 9, 10. This one is kepala. But here, here if follow this one, like we said, so we start at 7 lah because we know up until 9, up until 6 here is correct. So I cannot use that lah. Okay, so we up until 9 is 6 is here, and then 7 we should have 7 here. So start from 7 must be left, root, right. So that's why I said here should be 9, here should be 8, and then this one should be no nodes, and then here 9, here 8, and then 8 will have 2 nodes, which is 10 and 11. That is my I think is correct lah. How about Noel and Kelvin?
I don't know. Maybe the one line only. They should change to.
One line.
And the 7 to 9. The one should change to 10 to 9. The line. The connection.
Here. Oh,
yeah.
Here, you mean here. This is, we delete this and then connect here.
Yeah.
Okay. So actually, never mind, because we also don't know this answer is either pre-order or in order. But I will double confirm this letter lah, because if we based on us, I will agree with the gem both of you what you have done lah. Okay, so I will agree with this pre-order and this in order. But I will double confirm later this answer is correct or not, and it is for which answer, pre-order or in order. Okay?
Okay.
Next week.
Okay.
Okay, so it is 10:23 already, so we take 5 minutes rest. So we meet again at 10:28. 10:30 lah, 10:30 lah.
Oh, okay.
Okay, so are you both here?
Yeah.
Okay. So now we see the example on how this will be coded in Java. Okay, so first we will have an interface for the binary tree. So remember, an interface class is the class that doesn't have, it has method, but it doesn't have the body. Meaning it is empty method, only have the declaration of the method, but doesn't have any operation inside that method. So all like this lah, we can see there are here public method that can be override later. Okay, so this is the interface. We have clear method step 3. So it will have difference. This step 3 can have here kan, it is actually, it have 2 parameter. So for the first step 3, it only has 1 parameter. The second is it has 2 parameter actually. So actually there are another parameter here, but it is copy paste error, I think. Okay, so another parameter here. Okay, so there are 1, 2, 3, 4, 5. 5 methods that can be override later. Right? Okay, so we use this interface. So I already uploaded the chapter 9 sample code in our Google Classroom. You both can download that and unzip and then see the example. So here we have binary interface. So there already binary, yeah. Here binary tree interface. So this is it. This is the interface. Okay, after that. Okay, so this is the example of data that we want to code using that binary interface just now. Okay, so this data has a character in each of its node. Okay, so we will have one client program that will use binary interface and binary tree class. Okay, so here we will have in our chapter 9, we will have binary tree class, which it is actually implement the binary interface methods, and then we can build the given binary tree. So we will build this. Using the class just now. Okay, so how we will implement this is first, we will code the leaves first. So where is the leaves? The leaves is D, F, G, H because it has no children. So first, we will code the leaf first. After that, we will moving up. So here from the bottom level, go to the upper level nodes. Okay, so after that, we will use the step 3 method from binary tree to code the next level. Meaning after, for example, here is E, B, and C. E, B, and C. Because it is one level after the leaf. Okay, so BEC. After that, we will use the set tree method also, but with different parameter to set the root. Okay, so we will see the example in here in our chapter 9. So here the interface of binary tree interface. So this binary class, it is implementing the binary tree interface, and then here is the operation of each of the set tree. Okay, so in binary interface, we don't have the body for that method here. So this is the another set tree, but with, sorry, it is actually has three parameter. One is the root data. Second is the left tree object for the binary tree interface, and then the another parameter is the also object for binary tree interface, but it is for the right node. So here we have set tree. It says that we can use the set tree for the first. So this is how this is what it meant by first we see that we need to set the leaf first, right? So D, F, G, H. So we have another class that actually implement this binary tree. So this is we called as binary tree driver. It is the client class. And then, so how we set the leaf first, D, F, G, H. So we use the set tree, but the set tree that only have one parameter. Okay, so first we set the, first we declare first lah, the object for the binary tree, and then we set first instance for this binary tree is D, second instance is F3, and then it is receiving F. The third instance is G3, and it is receiving G. And then after that, the fourth instance is H3, which is actually receiving the H nodes here. D, F, G, H. So there are four leaves. So what we will do when we do the coding is we code or we set all of the leaves first. We declare and we initiate first. And then after that, we also need to initiate empty tree. This is when we need or when we need to code an empty children if it has no children lah. Okay, so after that, we proceed to the upper level, which is EBC. EBC. So how to code that is by we declare the object for the binary tree, and then we set this is what is the content of that node, and then what is its children for the left, and then what is its children to the right. Okay, so for E3, its left children is F, and then its right children is for E. Remember here, CC. For E, it has F children to the left, and then G as the children in the right. Okay, so we proceed with B and C also. So B, it has D and E. And then C, it only have H to the right, and then it has empty tree in the left. So that's why we put here empty tree. Empty tree meaning it doesn't have any value You see here, we only declare it, but we didn't initiate the value for that node. Okay, so after that A, we proceed to the A, which it has B and C. So that's why we have B and C here. So this is how it is coded. So if you want to see what happened during the step 3, you need to go to binary tree lah. What happened? So this is for if you just set the step 3 with one parameter, then it only will initiate and it will give value to the object. After that, if you see in the step 3, it is actually referring to the private method here. So this private method receiving 1, 2, 3, 3 also the same parameter like it will receive. Okay, so what it do is this code. When the left tree is not null and then the left tree is not empty, then you set the root. Okay, so the right also it is doing some checking. If the right tree is not null and the right tree is not empty, then set whatever the root it is passed to that method lah. Okay, so if we run this. Root of tree that contains A. Okay, so it will not show you the diagram. It will show you the order of the visit. Okay, so it will visit D first. It will visit D, F, G, H first. D, F, G, E. Okay, D, F, G, E, and then B, H, T, A. So who can guess what type of traverse that it implement here? D, F, G, E.
In order.
It says post order. It says post order over there, isn't it?
Yeah, post order actually.
Oh.
Yeah, it is already indicated here. Post order. Sorry, yeah, but ngam lah. We are guessing it right, except for Noel just now lah. You what guessing in order kan? But it is actually post order because if you see D, F, G, it is going from the left, right, and then baru pergi the root D, F, G, E, and then after that B, and then H. It didn't go to A. If it is in order, then it will go to A. But because if it is post order, then it go to H, and then after that C baru A. So this is the example of post order implementation. Okay, so we proceed with. So later you explore, maybe you can create another functions which is for in order and pre-order. But we see later lah. Maybe I think in our practical, because I haven't checked your practical lah. Maybe in your practical it is to implement the pre-order and in order maybe. So we see later lah. But maybe you can explore first lah. And then we proceed to so this is the sample code that I showed just now, the driver for the client that will access the binary tree. See, so this binary tree is implementing the interface. It is implementing the method inside the Java. So, why we learn this binary tree? So actually, this binary tree can be used to code some expression, meaning mathematical expressions. So this is the example how we can use binary tree to code the mathematical expression. Okay, so this is the one example of implementation example of binary tree implementation, which is to code the expression, mathematical expression. So an expression tree represent an algebraic expressions whose operator are binary. So this is the operator. This is the operator. This is operator. This is operator. All of these operator multiply, plus, minus. It is the algebraic. I don't know if I pronounce it correctly lah, but it is I pronounce it algebraic. Okay, so for example, this is the expression tree for 4 algebraic expression. 1, 2, 3, 4. Okay, so we see here for A divided by B, we can just use in order traversal. A go to the node to the root. So this is in order lah, in order. A left go to the root and then go to the right. So this is in order traversal. For this one, when you see this process, this expression, which expressions you should do first? Either the multiply or plus.
Multiply.
Multiply. Okay, so that's why we have another suborder, a subtree here, which is to express the multiply first because it needs to be calculated first. So by that, we are using we are using also the in order because A multiply with B. So this is subtree and it is using in order traversal. After that, this subtree using the same or traversal, it will go to the root, which is here, and then it will add here. C. So this is the combination of in order and in order. Both operation here is in order traversal. After that, for this expression, which need to be calculated first, multiply or plus?
Plus.
Okay. So, because we need to calculate this first, so we have here, this one will be operated first, B plus C, and then after that, it will be multiplied with A. Okay, so you see later why I explain this one by one. And then after that, for this, it is the a little bit complex, but we need to the mathematical rule. We need to solve the one in the bracket first. But in this bracket, they are plus and multiply. So by the mathematical rule, we need to complete the multiply or divide first, then baru the plus or the subtract. Okay, so that's why C and D here. C and D first. And then after that, it need to be added with B. And then after that, that process will need to be multiplied by A. All of this need to multiply by A. And then after that, the sum of all the result of all of this process will be divided by E. So the root will get the main operation inside it, meaning the last operations. For example, here this is very simple. That's why it is just like this lah. Okay, but for this, the root will take the last operation. For example, here because this is need to be done first, and this is the last. So that's why plus here. Here, this is the last operation between multiply and plus. Multiplication is the last. So that's why multiplication is the last. Here also, the last operation that we need to do is the divide. So that's why divide is here. Okay, so it is actually explaining this. An in-order traversal of an expression tree visit variables and operator in the tree in the order in which they appear in the original infix expressions. So this is what it means actually with this. It is the in order lah. This is the in order. After that, a pre-order traversal produce the prefix form of the expression. Okay, so okay, so in order traversal of an expression, visit variables and operators in the tree in the order in which they appear in the original infix expressions. So it is here. It is the original. It doesn't need it. It didn't involve any expressions. Okay, so the pre-order traversals produce the prefix form of the expressions. Pre-order. Pre-order, it must be above first. Pre-order traversals produce the prefix. It says here, pre-order traversals produce the prefix. The prefix is here. Prefix meaning the first operation that need to be done. So the prefix here is here. A multiply by B. A multiply by B. Pre-order is above and go to the right, to the left and the right. And then a post-order traversal produce the postfix form of the expressions. If you see here, the postfix is meaning the last operation is the first need to be done first. So if you see here, B plus C is actually at the end. Prefix is the operation that needs to be prefix is at the beginning. Postfix is at the end. Okay, so if you see here, this is the prefix because it needs to be done first. And then for this expression, the one that needs to be done first is the postfix. which is B plus C. So this is postfix, this is prefix. So it says that the postfix form of expression, it is done by post-order traversal. But we see first, either it is really post-order. Post-order is B, right, left, right, above. Left, right, and then go to above. Meaning it needs to be, it needs done this first and then go here. Okay, so, but maybe you won't understand now because I only, I also, yes?
Actually,
You,
I
you can
understand.
understand that? You can understand that?
Yeah.
Okay, good, Noel. Because I'm not good in explaining in English, bah. So that's why. But I know that this is actually what we call as prefix. 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 Yes, prefix. Prefix. This is suffix. And then this is actually infix because it only have only one operation in between the two. It is in the middle. I mean, because it is the only operation, that's why it is in the middle. Infix meaning the operation inside, in the middle. The prefix is the operation that is needed to be done, and it is at the beginning of the expressions, like this one. The postfix is the expression that is at the end of the expression, and then it need to be done first. So that's why this is postfix. So it is actually what it means by a post-order traversal, produce the postfix form of expression. Okay. So because we have only 2 minutes, then I think for this one, we will stop up until here, traversal of expressions tree. How we express the expression tree using the binary tree. So we up until here. So here is how we will implement the binary, the expression tree. How we will implement the expression tree punya code. But we will cover this next week. Okay, so we up until here lah. So do you have any questions, Kelvin and Noel?
No.
No.
Not yet lah kan? Okay, so if no, then we proceed. We will meet later on our practical. We will continue the last week practical, which is the sorting. Okay, so see you later. 2:30.
Okay.
Bye.
Okay. Thank you, Mr.